Okay. A car of mass 1,000 kilograms travelling west at 20 meters per second crashes into the rear of a stationary bus of mass 5,000 kilograms. The vehicles lock together on impact. Show calculations to test whether or not the collision is inelastic. So, in real life, we would assume that this would be inelastic. There's going to be noise. You're going to lose energy due to noise, okay, at the very least. But we need to prove this physically. We need to do calculations to prove that this calculation is inelastic, okay? Now, kinetic energy is not always conserved in a collision, but something is. Any ideas? Momentum, very good. Momentum is conserved. So, this is something to keep in the back of your mind, because for this collision, we need to work out our initial kinetic energy and our final kinetic energy, and we need to compare them. If they are the same, it's an elastic collision. If they're different, it's an inelastic collision. Okay? But our final kinetic energy, it doesn't tell us the speeds that anything's traveling after the collision. So how can we possibly work out the final kinetic energy if we don't have speeds? The way to work out those speeds or the velocities is conservation of momentum. Okay, so we need to use momentum first to work out the speed that everything travels at after this collision. So, our momentum before, so initial momentum. So our car is traveling with a speed, our bus is not. So our bus is stationary. So our initial momentum is 1,000 multiplied by 20. Now, even I can do that. Oops, 20,000 kilogram. Oh, come on, stop working. All right, while I fix my pen. So 20,000 is our initial momentum. Okay, so now we need to work out our final momentum. So our final momentum, we've got our, oh, there we are. Kilogram meters per second. Okay. Okay, so our final momentum. Our car and our bus have locked together. That actually makes things a little bit easier. P final. Oh, my pen's gone all messy now. I don't know what's happening. Okay. P final. So, again, mass times velocity. MV. Okay. Sorry, excuse the writing, I'm blaming the pen. Okay, so our mass now is 6,000 because our car and our bus have locked together. Okay, 1,000 plus 5,000, we've got 6,000 for a mass. We don't know our velocity. But we do know our momentum is 20,000 because momentum is conserved. Okay, so we can work out our velocity. So 20,000 over 6,000. Is going to be 3.33 meters per second. Okay. Yeah.
You could use, it's probably the same thing, you could have used M1 U1 plus M2 U2 meters per second.
Absolutely. Yep, absolutely you could. Okay. So this passes the common sense test. Our car is travelling at 20 meters per second, it hits something, and they both travel at a slower speed. That makes sense. So we have our final velocities. So now let's work out our kinetic energies. So our initial kinetic energy is 1/2 mv squared. 1/2 times our mass, because our bus doesn't have kinetic energy. Our bus is stationary. 1,000 times 20 squared. What's that? 420,000? Is that right? No. 200,000, yeah. 200,000 joules is our initial kinetic energy. Our final kinetic energy. Okay, our final kinetic energy Again, we've got our mass, they've combined, and we know our speed because we had to calculate it down here. So 1/2 mv squared, 1/2 mass is 6,000, multiplied by 3.33 squared. And I get 33,327. Something like that. And so you can see this, as we expected, is an inelastic collision. Okay, we have lost energy. Our initial energy was 200,000 joules. After the collision, we have much less energy than that, so we have an inelastic collision. Okay? The thing to remember about these sorts of problems, you must know the speed of everything after the collision. If you don't know the speed of everything after the collision, you need to use your momentum equations to figure it out, because momentum will always be conserved in problems like this. Okay? I'm going to leave my working on the board for a second, but